So today we'd like to talk about the thermal production of light. What this refers to is that objects that are hot are going to give off light. This is called radiation. And we are going to look at some stars of different temperatures and look at the quality and the quantity of the light coming off of the star. So we start with stars that are relatively cool. And by cool we mean about 1500 Kelvin. And when we watch this star, we will occasionally see light come off, infrared and red. When we increase the temperature of the star a little bit, we start to notice more light coming off, and we start to notice higher and higher frequencies of light. We start to notice that in addition to the red, we might occasionally get a yellow or a green or an orange. Okay, and then as the temperature goes up even higher, we can see even more light coming off. We've doubled our temperature. We started at 1500 and we went to 3000. Doubling the temperature causes the total power of the light coming off to go up by 16 times. Okay, so small changes in temperature create a big difference in the amount of light. And you can see by the time we double it again to 6000 that the amount of light is overwhelming. And we can also see that we are getting a wide variety of different types of light. Some reds, some greens, some yellows, some oranges, some infrared with the long wavelength, and some ultraviolet with the really compressed wavelength. We can reproduce this in the laboratory by having a light bulb with a wire filament attached to something where I can change the voltage getting to the light. Right now the filament is at room temperature and it's not glowing in any color that we can see with our eyes. Okay, when we start to increase the voltage, we eventually will get this wire hot enough that it starts to glow. Initially it will glow red, just like we saw with our star, where it's giving off some red, but also lots of infrared. As we make the voltage higher and higher, you see it getting brighter and brighter. We see it changing from red to white. It's white because it's giving off lots of different wavelengths and in a pretty high intensity of all the different visible colors. You can see when I lower the temperature again, we go back to the orange and back to the red. At some point, we're going to see it stop glowing. Realize it's still giving off light. It's just so cold that the light coming off is mostly infrared light. So there is a direct connection between the temperature of the object and the type of light coming off. So if we can monitor the light that's coming off, we could figure out the temperature of that object. The first person to find the connection between temperature and the type of light is this gentleman. You can see he's from what then was Prussia. You can see his years. And what he did is he looked at the light coming off of objects at different temperatures. Here we happen to be at 5500 Kelvin. He looked at the light that came off more so than any other color. It's called the peak color or the peak wavelength. And what we do is we would just trace it down and see what wavelength comes off more than any other. One way that we could separate the light into the different wavelengths is by sending it through a diffraction grating, which we learned about before. And we can see that this color comes off more so than any other. If we lower the temperature, you'll notice how it shifts to higher wavelengths. Higher wavelengths would be in the infrared range. Okay, so the colder ones shift to higher wavelengths. Okay, and you can see as we raise the temperature how it shifts back to the visible, to the red, to the yellow, to the green, to the blue, to the purple, and eventually it shifts into the ultraviolet. Okay, so there's a direct connection between this temperature and the type of light that comes off. Okay, now when we plot this out, it turns out that it's an inverse relationship. So the connection between temperature and wavelength is an inverse relationship. Higher temperatures give you a shorter wavelength. Lower temperatures give you a higher wavelength. The formula would be y equals some number over x. X is temperature, y is wavelength. And again, it's the peak wavelength because there's going to be all kinds of different wavelengths coming off. And we figured out, that as humans, figured out that the graph constant for this experiment is 0.002898. Okay, so this equation will allow us to figure out temperature if we measure wavelength. If we measure temperature, we'll be able to figure out the wavelength. Okay, so it ties together temperature and wavelength. Okay, the second equation that came out of all of this was done by Boltzmann, who we saw earlier this year, and Stefan. Okay, sometimes called the Stefan-Boltzmann relationship. And what we have here is temperature again on the x, but this time we have total power. How much total energy per second is coming off of our object? And it turns out, even though it looks like a squared relationship, it turns out that it's actually to the 4th power. And that's why when we double temperature, we get 16 times the power for the light coming off of our object. Okay, the other factors besides temperature are surface area, a thing called emissivity, which is kind of like the efficiency at which it radiates. It can be as low as 0, which is extremely rare, or as high as 1. 1 would mean 100% efficient. This guy here is a constant, and this time the constant is 5.67 e to the -8th. And again, P does not stand for pressure, it stands for power, which we measure in joules per second. So this equation lets us predict the amount of energy coming off an object per second. It depends upon the temperature, it depends upon the surface area. Every square millimeter is another spot for energy to come off. And it depends on a universal constant, which is 5.67 e to the -8th. And then some property of the material, which describes how efficient it is at giving off radiation, giving off light. Again, that E value is called the emissivity, and it ranges from 0 to 1. We will practice some problems with these tomorrow. I just wanted to introduce you to the theory today. So again, this equation lets you predict the total power. This equation relates the temperature to the wavelength that comes off most prevalently. Okay, the wavelength where you get the most coming off. Okay, the most common wavelength. We call it the peak. All right, so anyway, guys, that's what I wanted you to know about thermal emission of light for now. Again, we'll take it a little further as we do problems tomorrow.